For most of you, or at least many of you, Curtis Wilson will need no introduction. For those who don't know, Curtis Wilson is an eminent historian of science. I personally learned an awful lot from some of his papers on Kepler. And he's here to talk about the lunar problem, and in fact a nub or two of the lunar problem.
Thanks. Thanks very much. I'm very honored and happy to be able to attend this Harbor Fest. For more years than I can rightly remember, Bill has been his spiritedness, his can-do-itiveness, his stick-to-itiveness really inspired me, and he spurred me on in my studies. This topic I'm going to talk about actually took its start at University of Western Ontario, I think in 1990. I tend to say 1891. I heard George Smith in a meeting here say something like this, that the first lunar theory to be free from serious flaw was the Hill-Brown theory. And I decided about that time that I needed to explicate that statement. Now, I met him by chance yesterday and discovered that he thought that statement was one he made out of reading Brouwer and Clemenson's Celestial Mechanics. He thought it quite wrong. I spent about 9 years explicating it, so I don't know how this will bear out. But the reason he said that was that in the Hill-Brown theory, as published in 1919, there is an empirical term, actually a great empirical term, GET. And Hill knew there was going to be, probably going to be one. Newcomb knew there was one that he couldn't get rid of. Brown tried to think his way out of this. They all agreed with George Smith entirely that there was something, well, they thought there was something missing. And that was discovered. And I'll talk a little bit about that. But I think there's something right about the Hill-Brown theory that we need to grasp. My book is coming out with Springer. They tell me now in July. I still have to get the page proofs from India. They're coming. Some young lady there promises them on page proofs on May 27th. Anyway, this title I'd better say something about. It's made to scare away casual readers, of course. The Hill-Brown theory of the moon's motion is coming to be an short-lived ascendancy, 1877 to 1984. Well, that's the Hill-Brown theory was accepted for the lunar ephemerides in the nautical almanacs of U.S., U.K., Germany, France, Spain, at least, in 1923. And then it was demoted from that role in 1984, 61 years. Prior to the Hill-Brown theory, the basis of the lunar ephemerides was Peter Andreas Hansen's theory, which was adopted by France and England in 1862. So it too had 61 years of being the basis for the nautical almanacs. but there's great difference because in most of the time that Hansen's theory was used, it was realized to be flawed in an important way. Hansen had used differential equations, deduced the terms from Newton's theory. His was the first such theory good enough to be the basis of the ephemerides of the nautical almanac. Always before, the nautical almanac had been based on large-scale comparison between the terms of the theory and observations. Whereas Hansen had introduced numbers for the constants in the theory early on. And what this did was to obliterate, to obscure the path of his deduction. You couldn't go back and look over things again and see where a mistake had been made. But the Hansen theory was known to be incorrect, it needed correction. So how you couldn't do it responsibly. I should emphasize that always before Hansen, the nautical almanac, starting in 1767, was based on comparisons with observation. And this, the first one the first theory on which the nautical almanac was based was that of Tobias Meyer, the tables of Tobias Meyer, who died in 1762 at the age of 39. So he was a print worker. He made a lot of observations of occultations of stars by the moon. He was good at observing. And he didn't have method of least squares. Nobody did, at least until the 1790s. Gauss thought he must have had the method of least squares because anyone with his head screwed on right would have the method of least squares. He didn't. Instead, the method was a sort of, we don't really know, but it's a method of combining equations of condition by subtraction and addition in such a way as to make the coefficient of, resulting coefficient of some terms large and that of other terms small, and then you neglect the terms that are small. And of course, it's liable to lead to mistakes. But Meyer seems to have been especially good at getting results out that were pretty good. His tables were revised in 1778 by Charles Mason and the Mason-Dixon line team, using 1100 of Bradley's observations, same sort of technique. Another revision was made by Johannes Tobias Berg in 1806, using 3,000 of Maskelyne's observations. Then the tables were revised again by Johann Karl Burckhardt in 1812, using 4,000 observations. We don't know how those, I don't know if we have any evidence as to how those observations were made, but the tables were revised somewhat as time went on, but there was always this dependence on observation. Hansen's was the first set of tables derived from the theory, ostensibly without any illegitimate use of observations. Now, Meyer has left a statement. Tobias Meyer derived a set of lunar theory analytically. And he wrote about why he did that. The theory, he says, I'm quoting now, the theory has this inconvenience that many of the inequalities cannot be deduced from it accurately unless one should pursue the calculation in which I have now exhausted nearly all my patience much further. My aim is rather to show that at least no argument against the goodness of my theory, of my tables, can be drawn from the theory. This is most evidently gathered from the fact that the inequalities found in the tables, which have been corrected by comparison with many observations, never differ from those of the theory alone, that the theory alone supplies by more than 1/2 arc minute. Therefore, it is evident that these small errors derive from the side of the theoretical calculus rather than from the tables. I think the conclusion to draw is that the trouble was one of slow convergence. The theory was not converging. And I'm not talking about true mathematical convergence. I'm just talking about practically. The theory didn't give you get to small enough terms fast enough. Now this slow convergence was also met with by other people. Euler, Clairaut, and D'Alembert in the middle of the 18th century devised derived theories from Newton's law. And the accuracy of their theories were between 3 and 5 arc minutes. That was not enough to get the lowest prize offered by the British Admiralty, which was £10,000 pounds sterling, a lot of money. But you had to get within 2 arc minutes, because then you would get the longitude at sea within a degree. These theorists also found slow convergence in deriving the motion of the lunar apse. All of them, using different procedures, got as a first figure about 1/2 of the moon's apsidal motion. The moon's apse, perigee or apogee, whichever you like, moves over 3 degrees a month. They got 1.5 degrees roughly. That's again a case of slow convergence. In 1749, Clairaut performed a second order approximation. He had had that idea in mind all along, but it was an onerous task and he kept postponing it. Then he did it and found that he got a lot more of the motion of the apse. And a little later, D'Alembert went through 4 stages to get different contributions to the motion of the apse, and then commented he couldn't promise that this was to go on converging. And as a matter of fact, that's the story of the whole lunar theory. You don't know really, I mean, you don't have a mathematician's proof that what we're doing is going to converge. Now, the trouble with, as I've already mentioned, but Hansen's theory was this lack of transparency. You couldn't correct it responsibly. You needed a systematic, I haven't mentioned it, you need a systematic way of getting higher order approximations. That was something that Laplace never focused on with any concentration. He made corrections to the lunar theory from causal reasoning. For example, he said we know the moon attracts the Earth's equatorial bulge and contributes to the precession of the equinoxes. Therefore, the equatorial bulge must attract the moon and do something to the moon. So he went about finding out what that was. But he was not at all careful about doing second-order approximations. Laplace in the Mécanique Céleste derives some second-order approximations for Jupiter's perturbations of Saturn, but he leaves out many that are bigger than those he computed. So he didn't know how to do it in such a way that you would get the bigger ones in order down to the smaller ones. Laplace was very upbeat about the chance of getting a theory that was good enough to a theory good enough to predict the moon as accurately as the empiricists were doing. Those who used the observations. But it just wasn't, it didn't give people an indication of how to get a systematic way of going about higher order perturbations. All of the work on higher order approximations starts with Lagrange. It starts with his notion, with his introduction of the disturbing function. This is a potential function from which you derive the forces in x, y, z directions by partial differentiation, or with respect to any parameter with which the force varies, by partial differentiation. And you could go from there. There's no difficulty about having second order partial derivatives with respect to these variables. And Hansen's whole theory starts from the transformation of what Lagrange had done. So he was getting systematic perturbations, but his theory was not transparent. That was the difficulty. Now, in the 1830s and onward, you find several people starting to try to do both things, have a systematic way of carrying out approximations and having it transparent, which meant you couldn't substitute numbers at an early stage. You had to carry the algebra through all the way. And really got awful. The most complete and elegant of these theories was that of Delaunay. He started around 1846. Two big volumes were published, 1860 and 1867, giving much of his theory. George William Hill, a mathematician working in the Nautical Almanac office, started studying this in the 1870s and was wowed by it. He wrote a little article to introduce Delaunay to his American colleagues, saying the method of treating the lunar theory adopted by Delaunay is so elegant that it cannot fail to become in the future the classic method of treating all the problems of celestial mechanics. The method of Delaunay stems from a man, René, who introduced the notion of using as variables the elements, 6 elements that Lagrange had introduced of an orbit, 6 elements. Binet was dependent on Poisson, so it's all Lagrange. Now, I'm going to put up a little bit of text from Hill's 1878 paper. He wrote 2 papers on the moon. And here he discovered, after all his enthusiasm, he discovered that there was a problem. Delaunay got to 7th, 8th, 9th order terms. These are 2 9th order terms here, here and here. 9th order in terms of the small parameters. Italic M is the ratio of the sun's mean motion to the moon's mean motion. That's about 1/13. And E is the eccentricity of the lunar orbit. That's about 1/18.5. When you actually multiply those things out, the terms, both these terms here, end up being less than 1. But that isn't the problem. The problem is, how big is the next term? It's not small. You need it to be a lot smaller than this in order to be, in a pragmatic way, sort of convinced that, okay, I'm getting somewhere. I can get the next decimal place. But actually what was happening was that Delaunay could not get the next decimal place. So he did something which Hill decided was rude. He took averages over the last few terms he calculated and said, well, that's the amount of increase here is going to be the amount of increase in the next term. And that just isn't so. I mean, it might be so approximately, but it might not. It might not be at all the case. Hill just turned thumbs down at this point and said we have to start all over again. And he turned to Euler's lunar theory of 1772 and studied that as an undergraduate. In this theory, Euler proposed dividing the inequalities into classes and according to the small parameters. 5 classes. You'll note that the first one has to do with italic M or Roman M. Hill will come to prefer, Euler had used Roman M. That's the synodic ratio of the sun's motion to the moon's synodic motion. It's motion of catching up with the sun. That's about 1/12, bigger number. And if you start putting the series in terms of Roman M, they converge a little more rapidly. Note that the second class has to do with the eccentricity of the moon. And has nothing at all to do with the sun. It's as though the sun, dealing with that class, the sun could be absent. Then the lunar inclination is just the fact that it has to do with the fact that the lunar orbit is inclined to be elliptic. E prime is the solar eccentricity, about 1/60th. It's just a small variation, was a small variation in the solar force. And solar parallax is about, I mean the parallax of the orbit, the lunar orbit with respect to the sun, which is about 1/390. So the first of these is the one that most importantly introduces the sun. I'll argue for that in more detail. I want to mention that in 1766, Euler's son, Johann Albrecht Euler, presented a memoir to the Berlin Academy entitled Reflections on the Variation of the Moon. It contains, there's a pronouncement here. I quote, "I dare assert that if anyone succeeded in finding a perfect solution to the problem of variation, he would scarcely find any further difficulty in determining the true motion of the real moon." I asked Ronald Callinger, who's a biographer of Euler, whether he thought that John Albrecht had written that, or did his father do it. Callinger said right away, "Oh, I think it was the father." It has the, well, not exactly pontifical quality, but this is the statement of somebody who's struggled with the lunar theory a long time and thinks this is the way to go. And he's right in respect to which I think I'm going to shift around for a moment right now and talk about Tycho and the variation. Tycho discovered variation in 1594. He wanted his observers to get the eclipses of the moon when the moon enters the Earth's shadow from the start, all through the time of the eclipse. Well, in 1590, the observers got there too late. They were celebrating or something for dinner, and the eclipse had already started. Finally, Tycho figured out what was going on in 1594. What he did was observe the moon. The moon will be eclipsed when it gets here if it's close enough to be ecliptic. That happens about twice a year. It takes about 7 days and 9 hours for the other things being equal. I'll explain that later. For the moon to go from first quarter to full. Observing when the moon is in here, Tycho discovered it was ahead of where it should be if we take out the two big inequalities which have been in lunar theory since Ptolemy. One is sometimes called the elliptic inequality, a horrible name in my opinion. But it's something that is observed because the moon, in going from its most rapid motion to its slowest motion, gets ahead and behind of where mean motion would put it. So you have this, I'll call it so-called elliptic inequality, going from perigee to apogee. It's not because people actually measured the size of the moon and said, oh, it's closer to the Earth now and farther away now. You couldn't do that very accurately, even after we started getting names of micrometers. But no, it was because the moon departs from mean motion by a lot, by 6 degrees and 17 minutes or so. That's the elliptic. Then the evection is a combination of two things, and that causes a colony discovered. It produces a deviation of another degree in 17 minutes. What Tycho was discovering was that when the Gestalt got figured out was that the moon is moving most slowly in D and C, first quarter, last quarter, and most rapidly the syzygies in the A, new moon, and B, full moon. And in between, it's speeding up all around the year, slowing down from there. And Newton came along and explained this beautifully. I'm going to change the diagram to make it better, more close to scale. This is a unfortunately poor diagram with a circle left out. But it's the same thing that we had. There's really a circle going through D, B, C, and A. And I'm making the lines to the sun practically parallel. In the first edition of the Principia, Newton said the horizontal solar parallax is 20 seconds. That would mean that if we take the radius of the moon's orbit as unit, then to get to the sun we have to go 171 of those units out that way to the sun. In the third edition, he says that the horizontal solar parallax is 10.5 seconds. That means that taking this as unit again, you have to go out to 100. I think it's 325. I've lost that. But anyway, by the 1760s, Euler was saying the horizontal solar parallax is 9 arc seconds. That puts us out 380 units. And today we have the horizontal parallax of 8.79 arc seconds. That means 389 units out that way. So we're going out along that way, and might as well make these lines parallel. And then let's take the difference between the force on the Earth at T and the force on the Moon at P. Okay. That difference symbolizes PS there. We can split into two components, one radial going through T, the other at right angles and practically tangent to the orbit. And we see that one of them is causing the curvature of the orbit to decrease, right? Because it's attracted to the Earth's force. The other is speeding the moon up. So the moon there's less curvature in the orbit all the way around to the feet. With least curvature right here. And we're speeding up to A and deceleration from A to D. That's exactly what Tycho found. Then the same thing happens over again. Now you're subtracting the greater force on the Earth from the lesser force on the moon. And the result will be a negative force out this way, which you can then split into components. What I'm trying to suggest is that the big inequalities, elliptic inequality, evection, being subtracted out, we're able to see by this discovery of variation something of finer structure occurring in the lunar and what goes on. And this variation, as it's called, Tycho just gave it that blanket name, is a finer tuned thing, empirically speaking, than the older inequalities don't use. Now, exactly what Hill thought, I don't know. He's given to concision, which I seem not to do. But anyway, he introduced some equations for this situation with the moon, sun, and the earth. I won't discuss them. He took these equations, these definitions of x and y, and those are chosen because he's choosing rotating coordinates at this point. And the x-axis goes from the Earth to the mean sun moving in the ecliptic. And he has the y-axis going at right angles to the x-axis through the middle of the Earth. And choosing these odd multiples, I as an integer, choosing the odd multiples of the angle nu times time, mean motion times time. He will bring it about that he gets a periodic orbit. That choice means that when the moon is on the x-axis, the line of syzygies, then it's moving at right angles to the x-axis. When it's on the y-axis, it's moving at right angles to the y-axis. And that will just keep repeating. So it's a periodic orbit. And it gets us an ideal periodic orbit. if, for instance, we perturb it a little. Well, I should have mentioned that in deriving those constants, he gets what looks very nice. That is, he gets A1 over A some variable here, A minus W. These letting the terms, he's approximating my trigonometric series. And he's getting what looks like very nice convergence. Really, 3 places at least at each stage. These are successive stages. To get the A sub 0, you have to introduce the mass of the Earth. Okay. Now, the introduction of, it tries introducing a little eccentricity into that orbit. Suppose that we introduce into the differential equations first x sub 0 and y sub 0, which are the coordinates for the variation curve that I've just been talking about. And then introduce x sub 0 plus delta y, delta x, and y sub 0 plus delta y. And you come out with these differential equations for delta x and delta y, where these are partial derivatives evaluated for the coordinates in the variation orbit. In other words, he has a variation curve, as he calls it, and then he introduces a little bit of eccentricity, a little bit of departure from it, and asks the question. He knows that that will produce a hump somewhere. There will be a maximum departure somewhere from the curve. And well, that will move because only if you have an inverse square force directed to the Earth will it stay fixed. But we now have, we know, sun activity. So the hump will move. How fast? Well, he computes it and finds he gets a value differing from the actual motion of the moon's apse by 1.43%. 1.43% greater. He knew he would get greater because he left out of account the inclination of the moon's orbit to the ecliptic, which the inclination decreases the effect of the sun on within the plane of the orbit. This is something as important as I can underestimate. Remember that Euler, Clairaut, Dollander on a first stage computation got 1/2 outside of it. Now he gets on a first stage calculation 1.43% difference from the observation. No one had ever come anywhere near that close. Now I'm going to must slight Brown, not going into detail about what he did. There's one who Brown received the gold medal of the Royal Astronomical Society in 1908, I think it was. president of the society gave an address, and among other things noted that he got this from a colleague in British Brown had always checked his results to see that they were differential variations of the variation curve. If I haven't made that clear, please ask a question. There's a variation curve that Hill has established. And then Hill has shown that a slight variation from that curve is going to produce an eccentricity, is going to, and the apse will move very close to what is observed. The strong guess, conjecture is, I would say, that Hill has found the right orbit in which to calculate this. And now Brown goes on to compute all the other deviations, all the other four classes of deviations. And these also are just infinitesimal, I mean nothing found by that, differential variations from that variation curve. That is, I think, the goodness of the Hill-Brown theory. But it had that starting, got the right starting. Apparently, if you're doing approximations, it's not, you can't start out with something way off and expect to have a converging theory as you go forward. Now, we know that from Poincaré and Kolmogorov, Moser, Arnold, and Moser, that the lunar theory doesn't converge. That is a simple consequence, I gather, I'm told, of the fact that we have the small divisor problem. It's all over the place in celestial mechanics. We get small divisors and they blow up coefficients of perfect pressure. But what seems to be possible is to get what Poincaré called an asymptotic approximation to what the moon actually does. And that should be the people who go into that seem to feel that we ought to be amazed by it. Now, I think I should, close off. In 1984, there was good reason to first I'll put this is Newcomb's diagram of what he called fluctuation. This is a sort of descendant from Hansen's empirical term, fudge term, where he got a supposedly Venus perturbation of the moon, but he just took the remainder of the observations, what's left over, and said, okay, that'll make my theory fit. Newcomb came along and said, well, maybe your theory fits 1750 to 1850 meridian observations, but I have observations on rotations of the moon of stars by the moon. Before then and after then, they don't fit. So you have to change it. And Newcomb didn't find, he despaired. He died in despair. In 1909. That problem was not solved before the Hill-Brown theory was published as tables in 1919. It still had an empirical Feinstrom in there. Brown had tried to find an explanation. He'd given a speech to the British Association for the Advancement of Science in 1914 and mentioned the difficulties. And Joseph Marmor, the Cambridge physicist, wrote an article saying the discrepancy is intolerable. Something should be done. And all the physicists seemed to gravitate right away to assuming the trouble was the Earth wasn't rotating uniformly. Well, they already had astronomical evidence that the Earth wasn't rotating uniformly because John H. Adams in 1853 showed that Laplace, in calculating the secular acceleration of the moon, had made a mistake. Laplace said there was about 11 arc seconds of increment per century in mean motion. And it was only about 5.7 or 6 arc seconds per century. How was the rest to be explained? Various people around me said, well, if the Earth is slowing down, that would produce an apparent acceleration. As a matter of fact, one has a good idea of how that happens. The moon raises tides, solid and liquid tides, and the Earth is rotating going faster eastward than the moon is. So if there's friction, the hump is carried eastward. The hump attracts the moon in the direction it's moving, gives it extra energy, pushes it into a higher orbit where its mean motion is less. This is complicated. But the friction slows down the Earth. So the Earth is moving more slowly, and we know that now. So the Earth was slowing down. Astronomers knew that. That didn't seem to put them to work trying to finding a new sort of clock on the Earth's rotation. But when H. Spencer Jones showed in 1939 that the fluctuations that Newton had discovered in the moon are also found in Mercury and other fast-moving objects. The proportionality to their respective motions. That clinched the argument. And astronomers started looking around for an alternative clock. And they invented something called ephemeris time. I don't have time to talk about ephemeris time. I think it was a mistake. But it was a lot of effort went into it. Meanwhile, the atomic clock was on its way. It was really in place by 1955. By 1970, it was getting to nanosecond accuracy. It was being established that shocks and gravitational fields and accelerated coordinate systems are slowed by either one or the other, relativistic dilation of time. And you have to start taking account of light time, the time light takes to get from where it starts out from a celestial body and gets to your telescope. You have to worry about the gravitational fields it goes through. You can't just take measurements from the telescope and know where anything is exactly. The shift of the ephemerides from the nautical almanac office to jet propulsion laboratory in Pasadena, finally settled in 1984. The reason for it was that, or a reason involved in it, was that jet propulsion people had started getting a third measurement into astronomy, the distance of bodies. They found from radar measurements that Mars was 700 miles closer to the sun than the astronomers thought it was. And then in 1969, they put retroflectors on the moon and started getting the distance of the moon by laser measurements down to a few centimeters. Show that the moon is actually receding from the Earth. I think that Gerald Clements just felt that the Nautical Almanac Office couldn't inject itself into this new culture with its new results successfully. JPL needed ephemerides that were accurate to get people to land on the moon and things of that sort. Kind of important not to be off by 300 meters or 50 miles. The last thing I want to go into is the attempts to carry forward an analytic integration of the moon's motion. Just do this in the most hasty manner imaginable. JPL was getting ephemerides by numerical integration. They were engineers, they'd always done it that way. It was a good way to go. And they discovered a lot of things doing what they discovered. For example, the 3 asteroids had an influence on the moon that was sufficient, that they needed to take account of it. The astronomers in the East didn't know it. There were other people, mathematical astronomers, who still were concerned with an analytical integration in which you actually get terms with coefficients and say this is the way the moon goes. First, Andre Dupree, using Lie transforms to carry out multiplications of series, he wanted to see how good Delaunay was, and he showed that Delaunay was pretty good. But he also was aiming at a much higher precision, 5/10,000th of an arc second, and ended up finding he had uncertainties of 1,000th to 5,000ths of an arc second. So this is still slow convergence relatively. He and some colleagues then thought they would do a 2-step process, and that's what Edward reports in 1978. the theory which they give the acronym SALE for is better than the ALE that agreed on. Then Martin Gutzwiller in 1979 is carrying forward the work of William Eckert, which my newly found friend, Mr. Ollie here, is working on in Toronto. And he carried through the development of the ephemeris from what Eckert had been doing to try to update the Hill-Brown theory. ELE, because of Eckert's lunar ephemeris, is its agreement with SALE is as good as ALE's. Then the Michelle Chapon-Trousset and her husband, Jean Chapon, developed a semi-analytical theory. I have to confess I don't really understand exactly the status of that theory. It's now, as it's been developed, it's the basis for the Renaissance d'État in France from 1984 on. But it's called a semi-analytic theory. And the last computer of analytic theory Peter Schmidt of the University of Cincinnati says that the Chapron theory needs another theory to confirm it, and he finally believes that he supplied it. Now his program is derived from Hill-Brown, as it starts using Roman M, synodic ratio, also as numerical, puts that into theory as numerical. Puts also M over massively, moon over massively, moon plus massively. That's that was measured with high accuracy by JPL. So they solved the main problem. The main problem was a term that Brown introduced. It's everything in the lunar theory except planetary perturbation and the effects of the non-spherical shape of the Earth and the Moon. And the conclusion that Schmidt draws, being able to finally to get agreement with the Chapon theory. The Chapon theory is based, is tested against JPL's ephemeris. So there's some kind of dependence there. This is a theory which is not, which is derived from the analytically all the way through, except for those numbers that are entered at the beginning. Schmidt concludes one is actually able to calculate a solution to a very high degree of accuracy. This is a consequence of the judicious choice of Hill's intermediate orbit as a starting point and the nature of the phase space in the vicinity of this orbit. It is possible to compute a formal solution in the sense of an asymptotic approximation, which matches the observational accuracy of the Moon's orbit. And Gutzwiller and Schmidt made a joint report in which they conclude that the Hill-Brown theory of lunar motion is one of the great achievements of celestial mechanics. Thank you. Sorry to take so long.
out of sheer selfishness, I let Curtis go on rather than trying to hurry him up and or cut him off because I wanted to hear how the story ended. But that means that we have very little time for question period. We have about 5 minutes. Alan.
I'm curious, did you look into the extent of Brown's Hill's influence on Poincaré's work in
Well, not really. I know that Poincaré praises Hill to the skies. You know, Brown in late life, there was some kind of little tension. He waited until Hill had died, a good many, or 20 years dead or so, and then pointed out that instead of using an infinite determinant, which Hill had used to get the motion of the moon's house, you could simply take an approximation of, let's say, 4 places, put it in the differential equations, and come out with 8 places, and repeat that as many times as you wanted. That is sort of crude, quick and dirty methods.
Newton's method, actually, in the 1671 math treatise. Not a differential equation, but in an equation.
So I don't know enough about what Poincaré was interested in 2 things about, I would say, about Hill, from what I know. One is the infinite determinants. I don't know what their future history has meant for anybody. The other thing is that Hill introduced the idea of a periodic orbit in phase space and then returning that. That is analytic continuation to get out to various variations of that. But that's what I'm trying to say is the Hill-Brown, the essence of the Hill-Brown theory. It's true that, as George pointed out to me yesterday, that there's this empirical term, and it was a dreadful problem to these people that we're talking about. I mean, they really suffered from it, and they couldn't solve it until there was a way of showing that, yes, the Earth jerks around as it moves around its axis, and change the air pressure over the Pacific, and the Earth changes shape a little, and that's a different speed of rotation. The core and the mantle apparently get teamed together at one time or another, and then apart. And that makes a huge difference. All sorts of things are going on, and people are studying it, trying to make sense of it.
Rob and then Bob.
So just very quickly, I wanted to make the point that modern computer algebra systems are under development now, continually following along. One of the early successes in 1967 was to redo the Delaunay expansion automatically and try and recover these kinds of things. And the techniques that you're talking about are themselves of interest not just in celestial mechanics, but in all kinds of other vibration analyses. And just to point out that the modern systems are up to computing with millions of terms. And there's just an enormous amount of interest in the tools themselves, not just in the physics of them, but the history is really quite interesting and for everybody.
Bill?
I was struck by that. I hadn't realized that the tidal current, the tidal effects. I'll just say the gross when the slowing down of the Earth at the time. That it was after, only after that they had found it in ephemerid, showing up in ephemerides for Mercury and the other planets, and not not just the lunar theory, that was what that you were saying it was at that point that they really decided to change the concept from using the Earth's rotation and started. That's really, that's a neat point, and I had not realized that.
George.
Can I just make an observation to Curtis? I understand the people at the time thought it was a great failing of Hill Brown, but in other places I've argued the greatest success of Hill Brown was to expose a discrepancy with a clear enough signature that we learn something new about the world. If you think the role of theory is to learn about the world, not just to sit out there, then the Hill Brown theory is the first lunar theory that enabled us to do that. And I think that's remarkable.
I'm afraid we're out of time. Let's thank Curtis once again.